Okay, good evening, everybody. For those of you from outside of Keele, just introduce myself. I'm Professor Mark Ormerod, Deputy Vice-Chancellor and Provost here at Keele. Those of you from within Keele, obviously welcome, very welcome as well. Particularly like to welcome Josep's family and friends to tonight's occasion. Just say a little bit about inaugural lectures. So inaugural lectures are an opportunity for the new professor to say something about their area of research expertise, and also an opportunity to profile research at Keele and in the discipline, in this case in the medical sciences. So before I hand over to tonight's lecture, I'll just say a little bit in terms of biography. So Professor Josep Sulé-Suso is Catalan, originally from Barcelona, and qualified in medicine and surgery in 1987 at the University of Barcelona, and then between 1988 and 1992 trained in oncology at what was then North Staffordshire Royal Infirmary in Stoke. And then between 1992 and 1995, Josep was a research fellow at the National Cancer Institute in Milan, in Italy, and in this period he worked on basic and translational research in tumour immunology. Then in 1995, Josep came back to North Staffordshire Royal Infirmary and Keele University, where he's been working for the last 22 years, combining clinical duties at the Cancer Centre at what's now University Hospital of North Midlands with his basic and translational research in the Institute of Science and Technology and Medicine here at Keele. Obtained his PhD from Keele in 2003 and was promoted to clinical lectureship in 2004, clinical senior lecturer in 2006, and obviously now to a chair position. Josep's research is in the area of cancer immunotherapy, cancer cell biology, and it includes translational research and clinical trials, uses vibrational spectroscopy and synchrotron-based Fourier transform infrared spectroscopy. We've had a run of lectures in music and philosophy recently, and as someone who's carried out infrared spectroscopy for many years, I'm actually very familiar with some of the research that's going on that we talked about today. And so Josep makes extensive use of synchrotron radiation at the Diamond Light Source, as well as in France, also carries out analysis of volatile organic compounds for cancer diagnosis. Josep's published more than 50 peer-reviewed publications, many in very high-quality internationally leading journals, and has a strong track record of obtaining funding, external funding to support its research, including from the Research Councils UK, from the EU, and various charities. It's an international reputation for his research, one of the founding members of the International Society for Clinical Spectroscopy, has a wide range of other significant international activities. So can I therefore, it's a great pleasure to formally welcome Josep Sulé-Suso, Associate Specialist and Professor in Oncology, and invite him to present his inaugural lecture this evening, Breath Analysis in Cancer Management. Are we getting there, or is it just hot air? Thank you very much.
Can you hear me? Yeah? Okay. Thank you for this introduction, Mark, and thank you all for coming today. I still remember when I received the letter inviting me to give this inaugural lecture. My first thought was, good grief, what am I going to talk about? This is a completely different lecture. It's not something I'm used to it. And my first thoughts were, okay, there's going to be in the audience people that don't know me, the people that know about my clinical work, the people that know about my research work. So I thought better divide this talk in 3 parts and in 3 questions. So the first question will be, who am I? Which, if I have to be honest, is a question of keep on asking myself more and more often, which is worrying. Then, what research do I do? And we'll talk about clinical research and basic and translational research. And finally, what do I teach? So who am I? Well, as Mark has said, I was born in Barcelona, a wonderful city, nice weather, nice food, excellent architecture. You can see here 2 of Gaudi's buildings, the Temple of the Sagrada Familia and La Pedrera. And for those who like football, we have one of the best football teams in the world, of course. And we have got the best football player at the moment. So, I was born there. There's a picture of me when I was very, very young with my grandparents, trying to feed the pigeons, and looking at my face, even for my young age, I was never very keen on pigeons. And my wife can confirm that as well. So I grew there in Barcelona. This is another picture of myself. This is an image of myself with a typical Catalan Easter cake, with all the feathers and the chocolate eggs. And every child in Catalonia at Easter will have this cake. In Catalonia, we have cakes for every celebration. For Christmas, for the Three Wise Men on the 6th of January, for Easter, for All Saints' Day, for St. George's Day, so loads of cake. It's so difficult not to put weight on there. And then when I was growing older, I thought, well, apart from eating cakes, what am I going to do in life? And I started to be very interested on the history of this gentleman's country. As you all know, this is the death mask of King Tutankhamun, which is held at the Egyptian Museum in Cairo. And I was very keen on archaeology and especially Egyptology. And I read quite a lot of Egypt and the history of Egypt and the pharaohs. But then one day I thought, am I going to spend the rest of my life in the desert, surrounded by mummies with whom you cannot have very long conversations? So I think, better change to something else. And at that time, I had several relatives with cancer. And I thought, well, why not medicine? So I decided to study medicine. Especially, I wanted to do clinical work with patients with cancer, but I also wanted to do research. For me, to do both was extremely important. So I studied medicine in Barcelona, and I just want to show you one of the hospitals where you can learn medicine. This is a Sant Pau hospital in Barcelona, and this is inside the hospital. So again, the architecture in our town is wonderful, so you can study medicine here, which is great. And for patients as well, it's very nice surroundings. So I studied medicine, and then at the end of my career, as I said, I wanted to do both clinics and research. I thought that that would be very difficult to do that in Catalonia, and especially in Barcelona, so I decided to move abroad. I started to look at possibilities to do both somewhere in Europe, and I ended up going to Sweden. This is Stockholm. The Swedish government offered me 3 months full pay in Sweden, learning the language, and after 3 months, I could just apply for jobs there or for training posts. And in fact, I was ready to go to Sweden when a friend of mine from the medical school who was already working in the UK said, oh, forget Sweden, it's too cold there. Come to England, you've got plenty of opportunities here. So I believed him, and I decided to come to the United Kingdom. I spent some time in Chippenham, in Wiltshire, with him, and then I applied for jobs, for training posts. And one day, I had an invitation to an interview in a place I've never heard before. A place called Stoke-on-Trent. I've never heard of Stoke-on-Trent before. I didn't know where Stoke-on-Trent was. We didn't have Google in those times, so I had to look at the map. So I came to Stoke-on-Trent. I had the interview with John Scoville, and he gave me the job. And I thought, oh, brilliant. It must not be too different. At the end of the day, it's an EU country, or at least it was an EU country in those times. Who knows in the future what will happen. And I thought I spoke enough English to understand the patients, and then I ended up in Stoke, and I have to say I really struggled with the Stoke accent. I had real trouble. There are two things that I really struggled. One was, as I said, the accent, and I could not understand why people from Stoke-on-Trent, they knew I was a doctor as soon as they have met me, because I used to say, how are you, doc? Doc? How do they know I'm a doctor? They just met me. And then I realized that that was not what they meant. In fact, it was a bit of a shock for somebody coming from Barcelona to Stoke. And one of the radiographers, I think she felt so sorry for me that she issued me this certificate. This is to certify that Josep Sulé-Suso has been awarded the Order of the Duc, Doctor Under Culture Shock. So that was one problem. One of the nurses tried to teach me how to say you cannot kick a ball against the wall and hit it until you bust it, but to this day it's impossible for me to say that. And that was one of the problems. The second problem I had is that at home, we're used to measure things with Celsius, kilograms, centimeters, and liters. Here you measure things in a completely different way. It was terrible. To measure in Fahrenheit, stones, inches, and pints or gallons, I still struggle after so many years. And I remember one of the very first few days I was on call. It was a night, I was sleeping. And one of the nurses called me and said, Josep, come to the ward, please. We've got a patient here who's not very well. He's got a temperature of 102 and a weight of 7. And taking into account I was half asleep, I thought, 102 Celsius and 7 kilograms. What patient is that, a roast turkey? I think she was taking me on. I didn't understand what she was talking about. And then I realized she was talking in Fahrenheit. But anyway, eventually I started working here in Stoke, and I worked with Rona Lindup, John Scoble, and Jane Williams. I couldn't get a good picture of Jane Williams. And I am very, very grateful to the three of them. They were excellent mentors. I learned a lot of oncology, and I will always be very grateful to the three of them. And then later on, Maury Brown joined us, and also Fauzi Adap, and from both I also learned quite a lot. So I spent 4 years here, and after 4 years I thought, well, now I know a bit about oncology. My next step is to learn about research. I want to do basic research, so I don't want to do it part-time. I want to just do full-time for 1 or 2 years and see whether I can learn about it and develop my career. And I was lucky enough to be offered a research post in Milan. Milan in Italy is a wonderful city. Again, nice food, nice weather, nice architecture. You can see here the Duomo, the cathedral in Milan. And Milan has got something which is extremely important for me. Milan has got not 1, but 2 football teams in the Premiership. So I had a wonderful time there. It was great. It was really good. There I worked with Dr. Giorgio Parmiani and his postdoc, Flavio Arienti. I have to say, Giorgio Parmiani is considered one of the best tumor immunologists in the world, even by the Americans. He was my mentor in research, and anything I know about research, I owe it to him, and also to his postdoc, Flavio Arienti, who is still working there. It was excellent working with them. They made me feel very welcome, and I learned a lot. And what did we do there? Well, the main work was tumor immunology in melanoma, which is a skin tumor. So what we used to do is have a patient with melanoma. We would get one of the tumors out. We would grow the cells in the lab. Then we would modify them genetically to produce proteins, let's say interleukins, for instance, which can improve the immune response to the tumor. And then we would irradiate the cells so they would not create tumors, and we inject the cells back into the patient. In parallel, some other people within our group used to work with mice and would do experiments in mice. The 2.5 years I worked there, I learned, well, first of all, what we got was just partial response. Patients with this type of tumor did not respond very well. The response rate was lower than 30%. And in many cases, some of the tumors will get smaller, other tumors will get bigger. But all of my period there, I learned 2 things. The first one was, what works in mice does not usually work in humans. The people who work with mice got excellent results. The tumors disappear. We work with humans, it didn't work. And then another thing, which is my personal opinion, is that quite often in research, we try to go too fast into a clinical application. We think that we have discovered something in the lab. We think it can have a clinical application. We go and treat the patients or give something to the patient, and it doesn't work that well. I worked there, as I said, for 2.5 years. We were pushed quite a lot by Dr. Parmiani. He used to say that we are competing with the Americans. They have got more money, they work harder, but they are not more clever than us. And thanks to him pushing me, I ended up with 9 papers in 2.5 years, which for somebody who has never done research, I think it was amazing. I couldn't believe it myself. And then one day, after these 2.5 years, I had a phone call from Stoke-on-Trent. Murray Bront and John Scoville rang me and said, would you like to come back? I said, well, it depends what you offer. I said, well, what do you want? I said, well, I would like to do clinics, but I would like to do research as well. And they allowed me to do 4 days clinics and then 1 day for research. So I said, okay, excellent. So I came back to Stoke-on-Trent. And the first thing I did is to do my PhD. With 1 day a week, I managed to finish my PhD in 5 years. And at this point, I need to thank Alicia, my supervisor. Alicia was not only my supervisor, but she has always supported my research, and I'm very grateful to her. And then, from then onwards, the rest, as they say, is history. So you know a bit now who I am. So, moving on, what research do I do? Well, I do clinical research, and I'm also doing basic and translational research. One of the things I'm very keen in clinics is to improve the way we provide information to patients, especially patients with cancer. If we look at the literature, many studies say that there is an information gap between the doctor and the patient. Sometimes, as a clinicians, we underestimate what patients want to know, but it works the other way around as well. Some patients don't want to know much, and they prefer to trust the doctor. And also, very important, sometimes relatives might feel excluded. And this is especially important in oncology and in radiotherapy. A patient with cancer who has to have radiotherapy, we would show them the CT scans. We would explain what the radiotherapy is about. We would tell them about the side effects and the possible outcomes. But they say they can understand it, but radiotherapy is a very abstract concept. Many of them don't fully understand. And relatives cannot go into the room where the patients have the treatment either. So I thought, well, can we improve that? And my thoughts were, if we could have a virtual reality system that we could show patients how we plan the treatment, they could see the room before they start the radiotherapy, the machine, and so on, maybe that would help them to better understand what treatment is about. And at this point, I need to thank Andy Moloney, who was the head of physics department, and he retired a few weeks ago, lucky him. So he came to me and said, well, we have got something here we use for teaching. It's a 3D imaging system with 3D glasses, like in the movies. Okay, so I decided to use it, and what it does is simply, it offers images in 3D. We have got a big room with a big screen, the patients wear these 3D glasses, and then we show them the room where they will have the treatment, the couch, the machine. You can move the room around, you can move the machine around. We can even put a virtual patient, and then we can explain to them how we treat them. For instance, this is a patient with breast cancer who's having radiotherapy to the left breast area. And you can, the area to be treated is in red. We've got the right lung in yellow, the left lung in blue, and the heart. Then you can move the machine, you can move the organs, you can add organs, you can remove organs, you can explain why some patients might have certain side effects. So we decided to use this system and start a pilot study. We wanted to include 150 patients. 2 patients declined because they said they had already received enough information. It was important for me to use the patient's own CT scans, except in one case. We had problems uploading the CT scans in the software. And then we show them, before they start radiotherapy, images of the room, the machine, and the radiotherapy planning and delivery. And we ask the questions to fill in a questionnaire. From the questionnaire, what we wanted to know is the need these patients had to better understand how radiotherapy is planned and given. And the outcome was that most patients had a moderate to high need to see their own CT scans, to understand how radiotherapy is planned and how it's given, to discuss how the radiotherapy affects the outcome and also the side effects. And this was another opportunity for these patients to ask questions. This study was done on a one-to-one basis, patient and relatives with a doctor or a radiographer. And this was the very first time in the world that this has been done. Then we had some feedback, and we had got excellent feedback, very positive feedback. But we all know we can never make everybody happy. There's going to be somebody who's going to be unhappy, and we also had negative feedback. So let's go for the positives. Most patients said that they had a greater understanding. It was interesting. It was reassuring. Very important, it reduced the fear factor. And also, it was useful to partners. I'm just going to put some of the sentences some of the patients wrote. So a picture is more powerful than words. I have now got a good knowledge of what the treatment involves. This is an excellent opportunity to be involved, and it reduces the fear factor. I think carrying on this before starting the radiotherapy is beneficial and reassuring for most patients. And it was a good experience for both patients and family. So the comments were very encouraging. But as I said, we had negative feedback. One patient who was not able to see his own CT scans because he had problems using the software complained that he would have preferred that. In fact, I remember one of the patients who had an artificial hip, and we showed him the CT scans. The first question, this patient had a prostate tumor. The first question was not, what is the prostate, but what is my artificial hip? He wanted to see the artificial hip. He was not worried about the prostate. So another patient said that images from a textbook would have been enough, which I fully disagree. Now, we always get the odd one. This patient wanted to use the mouse himself. He wanted to use the software himself. It was a nightmare. He said that he wanted to be more involved by using moving the images and so on. And another one said that he was happy to see the standard CT scans, which I disagree to that. But there was something that many, many patients complained. In fact, so many patients complained that I lost count. Many patients said that this system reminded them like being in the movies, but many patients complained that we did not provide popcorn. At the end of the day, I told them, what do you expect? This is the NHS. So, the study is completed. The study was published. It has raised a lot of interest worldwide. In fact, radiographers from the department and myself, we were asked to do a webinar in which we would explain about the results of this study and our expertise to people from Canada, States, Europe, all the way to Australia, New Zealand. And very interesting, some of the radiographers thought that patients with prostate cancer who have seen this before starting the radiotherapy were more compliant with the treatment. A patient with a prostate cancer, before he has the radiotherapy, he has to drink lots of water and he has to hold the water. That's fine at the beginning of the radiotherapy. But towards the end, when you have got inflammation in the bladder, it's very difficult. So some of the radiographers said, look, these patients are holding the water better. So we have now started a randomized study in which we put 170 patients in one group where we are going to show them this information in 3D before they start the radiotherapy, and then another 170 patients will see it at the end of the treatment. This study started not long ago. We've done a preliminary analysis, and it would seem that those patients who see the radiotherapy in 3D before they start the treatment are able to hold the water better. That might translate also to reduce side effects, but we don't know yet. So, moving on. The next step is basic and translational research. And here I want to talk about two things. First, spectroscopy, and then on-breath analysis. This is not a UFO in somebody's garden. This is Diamond Light Source. This is one of the main research facilities in the UK. It's based at Harwell campus in Oxfordshire, which also holds the Central Laser Facility and the European Space Agency. And this is just a racetrack for electrons. what you have is electrons going around all the time in this direction at a speed very close to the speed of light. And if you have got electrons going in that direction like this, nothing happens. But if they move and you bend the path, they produce light. So then we use this light that is focused onto laboratories to do research. And the light which we use goes from the X-rays all the way to infrared. And these are the laboratories within the synchrotron. This is the infrared laboratory. I was the chairman for the working group that oversaw the construction of this laboratory, which has been very successful. People work here not only in biomedicine, but they also work on environmental sciences, plant biology, and even archaeology. I was also a member of the research committee of the French synchrotron. This is in the south of Paris. And the work there that we did is to oversee the research that was done, allowing people to come to do research based on the quality of their applications. And at present, I'm also advising the infrared laboratory at Alba Synchrotron, which is near Barcelona. So, what do we do in these labs? Well, first of all, you have to apply to work there, and you can only submit 2 applications a year. If you are successful, you would have maybe 3 or 5 days. And a diamond light source, only 50% of the applications are successful. And that means you have to work very, very hard, especially the PhD students start at 9 o'clock in the morning and they have to carry on work until 12 or 1 o'clock. And they do work hard, although sometimes there are some exceptions, and they do fall asleep. But it seems a diamond light source has got good provision for those students who don't work hard enough, which I have to say we don't use that often enough. So, what do we do there? Well, we use infrared light to study cancer cells or tissues, and that gives us information about lipids, proteins, and nucleic acids. Now, this is quite boring. This is one spectrum of a cell. But if you do mathematical models, then you end up with something like this. You have got the lymph node here that contains 2 areas with metastatic cancer. And using mathematical models, you can do a chemical map of the lymph node using, or identify the areas with cancer. The aim is to use these powerful machines to study single cells to identify markers that could differentiate between cancer cells and normal cells. And if that is the case, then we can use these instruments, called benchtop instruments, which can be placed at any pathology department, and we could develop automated systems in which you can put the tissue sample or the cell sample. The machine would analyze the cells at single cell level and tell, okay, this sample is negative, therefore the pathologist doesn't need to work about this. This sample is positive, then the pathologist can look at that sample. The aim is to reduce the workload of pathologists. The work I've done using both the French and the British synchrotrons over the last few years has led to quite a few publications, some of them quite high impact factor journals. So this is spectroscopy. Moving on, breath analysis. Now, breath analysis I am very interested in breath analysis because it could be a way to diagnose cancer or even to help the management of cancer. This is nothing new. That goes back to many, many years ago. About 4000 BC, Hippocrates already noticed that some patients had a special smell, some patients with certain diseases. Even in traditional Chinese medicine, there are reports that people try to diagnose disease through breath. But it was not until 1784 that Lavoisier described the respiration. That is, we consume oxygen and we eliminate CO2. At that point, some people wanted to study the breath of animals, as this cartoon shows from 19th century. And I think they were glad the Royal Society for the Protection of Animals was not there. Otherwise, they would have been very happy with this type of experiments. And then moving on, in the 1800s, acetone was described. And then Ansted identified ethanol. not realizing how important would that be for drink driving. And then more recently, there's some studies that suggest that there could be markers of lung cancer. We also had the first electronic nose in those times, in which the small machines that you could breathe into the machine and would tell you whether you have cancer or not. Or at least those companies who made the machines used to say, nothing is proven yet, in my opinion. More recently, people have had some interest in dogs. Now, it seems that dogs can smell cancer, and the reason behind that is as follows. First of all, the human nose has got 400 types of receptors, and we can discriminate over 1 trillion different smells. If you think this is amazing, just wait. A trained dog has got 1 million times superior sense of smell than the human nose. So it seems that there is something there that dogs might be able to smell cancer. And this is in part because the nose from dogs has got more than 100 million olfactory cells. So it's very powerful. I always wonder whether the nose of a Great Dane is better than a Chihuahua, but there are no studies to confirm or negate that so far. So at Guy Hilton, we are doing some research on breath analysis. We're not using dogs, of course. We're using something called the selected ion flow tube mass spectrometry, or SIFT-MS. At this point, I need to thank those people who have developed this instrument, David Smith and Patrick Spanel. David Smith here from Stoke and Patrick from the Herovsky Institute in Prague in the Czech Republic. And this is a SIFT-MS. It's portable, in inverted commas. They say it's very portable, but can be taken to the lab, can be taken to hospital, can be taken to theater. And that's the way it works. Very briefly, you have got carrier gas, helium, then you inject ion, H3O+, which then you inject the breath of a patient. There is a reaction, and then you can measure the final product. That's how it works. And the advantage is that you can use it for research. You can grow cells in these collagen gels. You can put cancer cells, you can put normal cells, you can put mixture of cells, you can put cancer cells with drugs, you can irradiate the cells, and then you can measure what it produces in the head space. You can collect the breath from patients using bags. You can take them to the lab, you can puncture the bag, and then measure the breath of these patients. Or you can just breathe directly into the machine, okay? You can ask the machine to tell you which components, which volatiles are there. You can choose the volatiles, acetone, acetaldehyde, ethanol, or you can just do a full scan, hold the whole thing. The advantages is, first, it's qualitative and quantitative. It's an online diagnosis. You can get the results within minutes. It's non-invasive, and this is very important, for instance, for children. You can measure the breath of children without being invasive and maybe help to manage certain diseases. It does not give radiation. Again, this is important. You can use this technique maybe to assess how well tumors respond to treatment. For instance, a patient with lung cancer, you give chemotherapy. After you've given the chemotherapy, in order to assess whether the tumor is responding or not, you can do a CT scan, you can do a chest X-ray, which gives radiation. Maybe this technique might be able to help you to diagnose or to assess whether the tumor is responding to treatment. And it's a good value for money. Once you have the machine, the running costs are not very high. The problem with measuring volatiles is that volatiles come from many places, not just from cancer. They can come from the blood, they can come from the muscles, they can come from infections in the airways or in the mouth, but also you have got exogenous VOX from pollutants or even from drugs. So it's not easy. So what we're trying to do is to see whether this technique could be used for cancer diagnosis and to assess tumor response to treatment. We use 3 cell lines, a normal lung cell line and 2 lung cancer cell lines. And what we do is we just grow them in these flasks in the lab. Then we put them in the bottles with the collagen gels, we purge the air, we close the lids, and after 24 hours, we measure the volatiles. And what we have seen is that cancer cells produce more volatiles, or some more volatiles in a higher concentration than normal cells. This is the ratio of volatiles produced by one of the cancer cells over normal lung cells, and then the same for the other cancer cell line over the normal cell line. So as you can see, it would seem that some volatiles are higher when you culture the cancer cells when compared to the normal lung cells. So we carried on doing some more research, but because we have got a hospital nearby, the next day was, okay, why don't we try something with patients? And there's always a pressure to try to do a clinical application. Although I said earlier on, I think we sometimes go too fast into clinical application. So we did a pilot study. I thought, well, let's start with a small number of patients. So we had 20 patients with lung cancer, which we measured the breath before starting treatment, and then 20 patients with skin tumors that do not metastasize. The breath samples were obtained in the morning. Obviously, patients had to rinse their mouth before giving up the sample. They couldn't eat or drink anything apart from water. They couldn't have a cigarette if they were smokers. They couldn't clean their teeth, and they would not be able also to wear the false dentures if they had false dentures. And then we took the sample in these bags, and we took them to ISTM at Guy Hilton, and we tried to see whether there were differences between cancer patients and normal patients. And the outcome was that there was no difference. We could not see any differences between cancer patients and patients without cancer. But what we saw was that some patients got a volatile in a high concentration. We look at this marker, and it came as acetonitril. Acetonitril comes from smoke, from cigarette, from smoking. So then we look at what patients were smokers, and as you can see here, we can measure acetonitril in patients who are still smoking, which is quite higher when compared to patients who never smoke or even ex-smokers. This has raised interest in the respiratory department. Some chest physicians have come to me asking whether this could be used, for instance, in lung transplant. Patients who need a lung transplant, they should stop smoking for at least 6 months or 12 months. Obviously, patients want the transplant, so some of them might lie and say, no, I stopped smoking 6 months ago, and that's not true. We don't have at the moment good techniques to assess whether they have stopped smoking or not. So we are trying to develop a study with the chest physicians to see whether this could help in lung transplant. So the next step was, well, let's go back to the lab. Let's try to do some more work and try to understand whether it is possible for this technique to help in cancer management. And what I wanted to understand is, when we have got a tumor, we all know that within a single tumor, you have got loads of different cells. Some of them are growing faster than others, some of them are dying, some of them are resistant to some drugs, others are sensitive, and so on. So I tried to develop an experiment in which we would see whether there were differences between cells. Now, to do that, we grew cells, CALU1, in the lab, and we use a drug called gemcitabine, which is a chemotherapy drug used for lung cancer, amongst other types of tumors. We grew the cells in the flasks. Then we cloned the cells. By cloning means to put cells in the plates at a concentration of half a cell per well, roughly. And then from one cell, you get a clone. So all these cells come from just one single cell. You can end up with maybe 5 clones. And then you could add the drug, gemcitabine in this case, and you can end up with sensitive and resistant cells. That means that you can study different clones that come from one single cell from the same cell line, but also you can study the effects of drugs on resistant cells and the effects of drugs on sensitive cells. And what we saw was this. This is the profile of volatiles for 4 clones. And looking at the data, my first thought would be, Houston, we've got a problem. If you can see here, there are big differences between different clones. And these cells come from a cell line which has been in culture for years, which in theory is quite uniform. So if we look at patients and we try to analyze or try to measure the volatiles released by tumors from patients, it's going to be difficult. And that's my view. I think we need more basic work. So the next step is, well, can this technique help us to assess whether tumors are responding to treatment or not? And to do that, we used 2 clones. One was resistant to the drug, so the cells keep on growing after 100 nanomolar of this drug. And another clone was sensitive, so the cells died when we incubated. Well, some of the cells died when we incubated with the highest dose of gemcitabine. And as you can see here, at 2 hours, there are differences between the clones incubated with no drug and the 2 doses, and the same for the sensitive clone. And at 24 hours, again, there are differences. This is telling us that, yeah, there might be differences, but before we apply this into clinics, we definitely need to do more basic work. We need to understand where these volatiles are coming from. We need to understand whether by modifying the metabolism of these volatiles, we might be able to diagnose cancer maybe one day. So, going back to the title of this talk, breath analysis in the management of cancer, are we getting there or is it just hot air? My personal opinion is that there is a potential, not just SIFT-MS, other techniques, GCMS, that could be applied to help cancer management, but more basic research is needed. I want to thank the people that has worked on these projects, Josep, Abigail, and Rashid. And just want to finish with the last question, what do I teach? One of the things that I'm very keen is for medical students to spend time in the labs. My personal experience is that we do not have medical students in the labs. They should spend time to realize whether this is something they want to do in the future or not, but at least give them the opportunity. So in collaboration with Paul Roach, we set up a master course in oncology, in which the plan was and is for these students to spend 4 months or 6 months in the oncology department, rotating through oncology and hematology, and then for 6 months doing a research project in the labs at Guy Hilton. That started last year, and at the moment we're trying to understand whether a master course would be better, or maybe a diploma, or MSc. So we're working on what would be the best way to bring these students. So now you know who I am, you know what I do, and you know more or less what I teach. During this talk, I've been thanking people. It would be impossible for me to thank everybody, doctors, nurses, radiographers, other colleagues who during my career have helped me a lot, and without them I wouldn't be here. I just want to thank a few people. First, Andy Garner. Andy Garner who has also retired, another lucky one. So Andy Garner has always been very supportive of my work. And Andy Garner, together with Alicia and Simon Davis, they supported me to become a professor. So I'm very grateful to him. And I want to thank my family as well. First, I would like to thank my grandparents and my mother. They always supported me, even when I decided to move and go abroad. And from then, what I learned is that if you want something in life, you have to work hard for it. And that's always been my motto. Obviously, I need to thank my wife, Jane, and my son, Michael, who have to endure hours and hours of me working, even working abroad, not being at home because I had to go to conferences, I had to go to meetings. So I'm very grateful for the support. And I also want to thank my family in Barcelona, who for obvious reasons couldn't be here. We've got here my brother, my sister, my nephews, my son, he's always there as well. And you can see here they are holding paper planes. This is a family tradition. On the 1st of January, we all get together for a meal, but before the meal, we make these paper planes and we throw them to see who can make them fly faster and as far as possible. But we cheat. This is done from a 10th floor balcony, so it's much easier. So, as I said, you now know who I am, what I do, and what I teach. I just want to finish by thanking you all for coming today, and thank you very much for your attention.